Welcome, and thank you for joining me again in my continuation of my discussion about the Euler's gamma function. We will look at those three important versions of this gamma function, and I will derive the Euler-Gauss formula again for you from the different perspective. As you remember, we discussed the improper integral version of the gamma function, very useful in the probability and statistics, where we calculate all statistical moments of the exponential distribution, very important. And Gauss made this wise move. He introduced this transformation. Again, when you make a move, you need to predict the outcome. Was a great transformation because ln functions continuous one-to-one, no ambiguities, and also it brings us the features of the special wonderful limit of the exponential function. So this is how Gauss modified this improper integral version, and he arrived into the Euler-Gauss formula. And today we will follow Euler. This green arrow will modify the infinite product of the gamma function into also the Euler-Gauss formula. So there are three versions of the gamma function. They are all useful in different situations. Number one, in complex analysis and probability statistics. Number two, it's a computation approach of the gamma function. Sometimes the improper integrals hard to calculate. This computational is just easier. All the products here, the power factorial, just take the limit, and that's your gamma function instead of looking at the improper integral. And the third version of the gamma function, which is the two-star formula actually, that is the infinite product, which has connection with the infinite series in calculus, and also it bridges us to the number theory. We are using infinite products in the number theory a lot. So this way, the two-star formula, gamma function, the one-star formula, gamma function, all come together into the Euler-Gauss formula. This is how we show that the two-star and the one-star formula actually are the same. They represent the same gamma function. As you remember, Euler the Great extended the domain of the factorial function onto the set of real numbers. That was the breakthrough. He discovered that the factorial as the integral 0 to 1 and also as this infinite product. And later on, Legendre modified it into the improper integral from 0 to infinity, t power n and so on. Consequently, n minus 1 factorial will be t just power n minus 1. And Legendre called it the gamma function. You may ask me, why did he call n minus 1 factorial, not just n factorial gamma function? You know, it really does not matter, just for the convenience, because later on we discover that the gamma function has the recursive property. If we look at this integral and integrate it by parts, and actually doesn't matter how, very easy. Every calculus book has that. You can look it up. So if you integrate it by parts, you will get this wonderful result. Gamma function will be equal to itself with the argument reduced by 1 multiplied by the sum correction factor. So you can integrate by parts anyway. Choose your u e minus t, the rest dv, or you can choose the u t n minus 1, the rest dv. Depending how you choose your u and v, you'll get one of those two versions of the integration by parts. And this is a great result because the gamma function is equal to itself with the argument reduced by 1. If you want to speak the computer science language, you would say the gamma function calls itself with the argument reduced by 1 multiplied by some correction factor. So the idea is that the gamma function is equal to x minus 1, gamma of x minus 1. And in each term, you can expand x minus 1 to x minus 1, x minus 2, gamma of x minus 2, and so on. You can reduce your argument up to any point you wish. Gamma of 1 is easy. Just plug 1 in here. We just a minus 1, 0 is 1. So integral of e minus x dx is just 1. You all know that. So if your input argument is a natural number, then gamma of x, natural x, will be equal to n minus 1 by x minus 2 by x minus 3, and eventually you will exhaust all your natural numbers and you will arrive to gamma of 1, which is 1. So finally, it's just x minus 1 factorial for the natural inputs. So finally, gamma of n is equal to n minus 1 factorial. It's a great result. The continuous nature on the left side, the discrete nature on the right side. So the gamma function connects the two worlds, the continuous world, the discrete world, the analog world, the digital world. This is what's great about this function. Euler, the great, developed that. And today we will look at the infinite product. Let's just modify it. For any a more than 0, it converges, not just natural, for any a real numbers. We can apply the Taylor series expansion in the powers of 1 over k, so 1 plus 1 over k. So for the general term, first of all, when apply Taylor series, what's important? The question of convergence. To show that this infinite product is equal to the limit, first of all, we need to show that it converges, then after that we'll modify it. Yeah? So the general term will be equal to 1 plus 1 over k, 1 plus 1 over k, power of a over 1 plus a over k. So applying Taylor series will be just 1 plus a by 1 over k over 1 factorial, yeah? Plus a by a minus 1 over 2 factorial here, multiplied by k squared, plus a minus 1, a minus 2 over 3 factorial k cubed. And so on, so it's a little o of 1 over k cubed. This little o notation of this infinite series, the higher orders of k, 1 over k cubed. And here I have 1 plus a over k. So it's equal to, just combine it together as 1 is k over k plus a. So it will be k plus a over k plus a minus 1 over 2 factorial k squared plus a minus 1, a minus 2 over 3 factorial k cubed plus little o 1 over k cubed over, I'll combine those two, k over 2, so k plus a over k again. And that's equal to, you can see the same term, it's just 1. So on the next line, I have actually 1 plus, now careful, the second term divided by the denominator, so will be a minus 1 over 2 factorial. Here, multiply reciprocal k will be on top, reduced with this k, so we will just k, no k squared, k multiplied by k plus a. So it will be k squared by plus ak plus a minus 1, a minus 2 over 3 factorial. Here will be, again, k cubed, k on top, so the k squared by k plus a. So it's actually k cubed plus k squared by a. And so on, so it's a little o of 1 over k cubed. So this is what we have as the result of this Taylor expansion. And now recall, note, when look at the infinite series now, when the infinite series k from 1 to infinity of ak, when this infinite series converges for k big enough, k big enough, and ak, say positive values, we have all positive values here. K is positive, k is counting natural number, then the infinite product k from 1 to infinity of 1 plus ak also converges. It's a special theorem in analysis. We proved it. Easy to prove it while involving the special limit of the exponential or logarithmic function. So it also converges. So by using this theorem, we can say that our infinite product converges. So hence infinite product k1 of 1 plus 1 over k power of a over 1 plus a over k converges. Yeah, you can easily see powers of k squared, k cubed, 1 over k squared converges, 1 over k cubed converges. Plus those, they make your series even smaller. So the larger series converges, the smaller series will eventually also converge. We discussed that in analysis, you all know that. So the infinite series converges. Now let's modify it. Now recall that the infinite product k1 to infinity of ak is actually equal to the limit of the partial product ak, k1 to n, when n goes to infinity. So we'll just look at the partial product of this infinite series and we'll modify it. So let's look at the partial product. Which is the partial product. High k runs from 1 to n, 1 plus 1 over k power a over 1 plus a over k is actually equal to the partial product k1 to n. Let me combine this, so it will be k plus 1 over k power of a over k plus a over k. This is the partial product, and it's equal to, let me expand it, when k is 1. When k is 1, we have 2 over 1, 2. So it's 2 to the power of a. It's actually 2 to the power of a over a plus 1 over 1, just a plus 1. Multiply it now. Now k is 2. So I have 2 plus 3 over 2 power of a. So it's 3 power of a over 2 power of a. Now divided by a plus 2. A plus 2. K is 2 now. Over 2. Now 2 goes up top. K is 2. Multiply it. But let me do one more time. So it will be, when k is 3, will be 4 over 3. 4 power of a, 3 power of a. Here will be a plus 3. A plus 3. K is 3. 3 goes up top. 3. And so on. And the last, the nth term will be equal to, when k is equal to n, so it will be n plus 1 power of a over n power of a multiplied by a plus n and multiplied by n. That's my partial product. I hope that's clear. Now look at this. We have nice simplifications, some reductions, fraction reductions, 2a to a, 3a, 3a, 4a, 4a, and so on, and so on. This diagonal reduction, which means that na will be here, will be reduced with that na, and this is what's left. What's left there? 1 by 2 by 3 up to n, which is n factorial, yeah? Almost there, yeah? Which is equal to actually, my numerator has products 1, 2, 3 up to n, multiplied by n plus 1 power of a over, here I have a plus 1, a plus 2, let's say, up to a plus n. This is my partial product. Now, my infinite product is actually equal to infinite product k from 1 to infinity of 1 plus 1 over k power of a over 1 plus a over k. That's this one. I'll just look at the infinite product. It's equal to the limit of that partial product, to the limit of it, when n goes to infinity. This is the definition of the infinite product. We all know that, we discussed that. So it's equal to, here I have n factorial, so kind of close to that form. Yeah? So it's n factorial. Look at this, n plus 1 power of a. Here I have a plus 1 up to a plus n. I hope that's clear. Now, if I multiply and divide it by n power of a, divided by n power of a, I have a very nice trend. Remember, it's equal to simple limit n plus 1 power of a over n. I can actually write them in this form. Power of a when n goes to infinity is equal to 1. You all know this from simple calculus. This goes to 1. And finally, we are arriving into this wonderful result. The limit n goes to infinity, n factorial, n power of a over a plus 1 up to a plus n. What is that? It's almost gamma function. One term is missing, yeah? It's just this infinite product. So which means it's equal to my gamma function multiplied by a, yeah? It's equal to my gamma function of a multiplied by a. We're almost there, and from here we're arriving at this wonderful result. A is a constant, positive, no problem, under the limit, n tends to infinity. A is a constant, in this case, for this limit, so I can bring it under the limit while dividing by a. So finally, gamma function is equal to this limit when n goes to infinity of n factorial by n power of a divided by, bring a term here, a plus 1, a plus 2, up to a plus n. We just arrived to this wonderful result. This is my gamma function evaluated in the computational form, gamma of a. And this is called the Euler-Gauss formula. Like I said, I called Euler 2 weeks ago. I told him, your highest knowledgeness, I came through the Russian mathematical literature, the German mathematical literature, through the math literature of some Asian countries, and they all, your highest knowledgeness, they call this formula the Euler-Gauss formula. And for some reason, in the English-speaking world, in the English mathematical literature, they all mention this formula. They say that it was developed by you, your highest knowledgeness, Euler, by Gauss, but they never explicitly call it the Euler-Gauss formula. And he told me, could you call Gauss, tell him the same thing and see what he says? The next day I called Gauss, and he told me, that's okay, if you want, you can declare it. So this is what I would like to tell officially. This formula has a name attached to it. It is called the Euler-Gauss formula. It allows us to calculate the gamma function from the computational point of view, because sometimes the proper integral is hard to calculate, sometimes the infinite product hard to calculate, even may not converge. If it does not converge, the limit will not exist. So the limit is kind of easier to calculate. Just the products, the powers, the factorial, just take the limit. And moreover, if we apply the gamma function to a plus 1, it will be equal to the limit of n factorial n power a plus 1 over a plus 1. Actually, it starts with a plus 1 and so on, and the last term will be a plus 1 plus n. N goes to infinity. Yeah? And if I look at the ratio of those two, so I'm trying to see if the recursive property is there, it's actually there. So then the limit, the ratio of those two, gamma of a plus 1 over gamma of a will be just equal to gamma of a plus 1, gamma of a will just equal to the same limit, the same index, and to infinity. So it's a limit. M goes to infinity of this divided by that. So a lot of simplifications here. N factorial reduce. So n a plus 1 over n a will be just n. And here I have this, and reciprocal goes up top. So I have here n a, and divided by a plus 1 plus n. This is what we have, a lot of simplifications, cancellations, fraction reduction. And what is that? The limit when n goes to infinity, n a over n plus a plus 1 is a constant. Obviously, it goes to a. And this is the evidence. It shows us again that the gamma function has recursive property. So from here, gamma of a plus 1 is equal to a multiplied by gamma of A. We just show the recursive property of the gamma function, not just using its improper integral version, the continuous version, but also using the discrete nature, the infinite product nature. I hope that was clear, interesting, useful, informative. I also hope you enjoyed it. Thank you very much. I'll see you again in my future clips. Thank you for your time again. Bye-bye.